Our next talk is from Katja, who...
Yep, that's me.
Perfect. And you're able to see how to share your screen now?
Yes, sorry, I was a bit confused about this. Let me see Microsoft.
No, we're all learning. It's a bit confusing.
Okay, can you see the slides?
Yes.
Without the notes?
No notes, just a beautiful picture of, I don't know where that is, but it's very pretty.
Of where we are, yes. So
lovely. Okay, well, I will hand over to you then.
Thank you. So I'm going to talk about evolution of neural complexity in division of labor, and this is work with Soheil and Federico, who are also here in the room, and we're all based at OIST, so in Okinawa, Japan. Okay, so some motivation for this work. So I guess everybody knows that our human brains are kind of bigger than would be expected from our body size, and there has been a marked increase in our brain size in evolution. And one particular hypothesis, so social brain hypothesis, claims that this is because of the complexity of our social life. However, at the same time, and that's a less known fact, our brain size has been actually shrinking over the past 10,000 years or so. So what's up with that? Well, there is a parallel work on social insects, where several studies have found that actually brain size of insects like ants and bees is negatively correlated with social complexity. And this has often been linked to particular social structures like division of labor. So from these two lines of research, there is another hypothesis that we could call a collective intelligence hypothesis that says that increased social organization can actually lower cognitive effort required of individuals, allowing for smaller brain sizes. So maybe also in the human case, because our society is so well structured, and we also have division of labor, this is the reason for the shrinkage of our brains over the recent history. So, as I mentioned, for instance, one trick that we have is division of labor. And that's why we're focusing on this particular example in this work. So the aims of our study are to actually set up different coordination scenarios and evolve agents in those scenarios, and then compare the resulting neural complexity of these agents. So specifically, we want to investigate coordination scenario in which there is task specialization, so-called specialists, compared to a scenario in which agents exhibit behavioral flexibility, and we call them generalists. So you can think of it as in the human society. So in the specialist case, everyone would have a specific role, like we tend to do. So we have cooks and we have doctors and teachers and so on. And we compare it to a scenario in which everyone can perform all sorts of roles. So everyone can be both a cook and a doctor. So that sounds already quite cognitively demanding. I think you can appreciate. And then we also evolve an individual agent baseline where there is no coordination required, so the task can be solved by the agent alone on their own. Then, so after we have evolved the agents, we want to apply a particular measure of neural complexity to them. And of course, here we can adopt a whole variety of measures of complexity, but we will focus on one of them that I'm going to explain in a few slides. Then, with regard to this measure, so what we're actually interested in is obviously the individual level complexity, so analyzing each individual agent and calculating this neural complexity. However, we also want to look at a somewhat more speculative application here, which would be the dyadic level complexity. So coming up with a measure that somehow can quantify the complexity of the collaborating agents as a pair. And this is motivated by this collective intelligence hypothesis, where if there is indeed some kind of higher level of organization emerging, we should be able to quantify this as well. So this is the more novel application here in the study, but also more exploratory. Okay, so the hypothesis in particular that we set up are as follows. So when it comes to the more simple individual level, we predicted that if the social brain hypothesis is correct, so the complexity is due to the social demands, we should expect the complexity of generalists and specialists, so both social conditions, to be higher than the complexity of individual agents. And if collective intelligence hypothesis is correct, we would expect the complexity of generalists to be higher than the specialists, because the specialist case allows for this offloading of cognitive effort onto the social structure. And then for the dyadic level, so again, if collective intelligence hypothesis has something to it, we should expect that whenever the agents are able to establish some kind of coordination, some way to solve the task together, it should not matter for the higher level dynamics how exactly the task is being solved, so the complexity should be comparable. So the methods, I'm going to briefly review them here and then explain in the following slides. So we chose a task that is based on a psychological study, just to make it a bit more ecological. We have implemented our agents with continuous time recurrent neural network and applied the standard evolutionary algorithm with fitness based on behavioral performance in this task. And then with regard to the measure of neural complexity, we specifically focused on Tononi-Sporns-Edelman's metric, which is a measure that tries to capture a balance between the integration and differentiation in the cognitive system. And we chose this measure because it tries to capture the complexity of the whole cognitive system compared to, for instance, looking at just separate time series of neural output or something like that. And also because it has good properties, so it's been found to correlate with adaptive behavior, to also increase in evolution as agents find a solution to the task, and so on. So this is an attempt. Of course, we could rerun this study with different measures and compare the results, but this is not the focus of this study. Okay. So the task environment is as follows. So we have a one-dimensional environment, basically a line, in which we have a target and a tracker, and the target moves on its own back and forth in this environment, starting always in the middle and reversing direction at fixed points. And then we have a tracker that is controlled by the agent. The tracker has two eyes, so it can perceive the target to the right and to the left, and it also has two wheels so that it can move right and left. And we're running for each generation 4 trials with 2 different starting directions of the target, so whether it goes first to the left or to the right, and also 2 different target speeds. So this is a visualization of the task, kind of for ease of visualization. You have it on 2 lines, but you should imagine that they're moving on 1 dimension. All right. So this is the agent network architecture. Basically, each agent in all our conditions is composed of 2 sensory nodes, which receive information about the distance to the target from the left and the right. Then we have just 2 internal processing nodes. And then they have two motor output units that then control the left and right wheel. And as I mentioned, so the evolution of the inner nodes is controlled by the standard Ekaterina equation. If you're interested in the details, of course, go to the paper. Okay, so how do conditions differ? So we have an isolated condition, as I mentioned, as a kind of baseline in which we have a single agent controlling the tracker. So in this case, the motor output of one of the motor units is controlling the left wheel of the tracker, and the other motor unit is controlling the right wheel. So straightforward implementation. Then we have the specialist condition. So we move on to the case of two agents controlling the tracker. And in this condition, basically one agent has a motor unit mapped into the left wheel, while the other agent onto the right wheel. And this is the case for all the four trials that they participate in. So the other motor unit can still be active, but it's just not doing anything. Then we move on to the generalist condition. So we still have two agents, and in half of the trials, the mapping is the same as in the previous slide, so as for specialists. However, in the other half of the trials, the mapping is reversed. So where the first agent was controlling the left wheel, now it's asked to control the right wheel, and the other way for the second agent. So that in this condition, all the agents have to learn to perform both roles, so left control and right wheel control. While in the previous case, they always experience only one direction, one role. Okay, the details of the evolutionary algorithm are here. They're not all so relevant. What I wanted to mention is so the fact that the specialists just perform the trials always in the same way, but they also are evolved separately, such that we're kind of evolving two separate populations. So the population of left wheel controllers and the right wheel controllers. And in all social conditions, in both of them, each agent is paired with 3 random partners for this task, so that they learn to play this game with different partners and not just always with the same one. And obviously the fitness here is to minimize the average distance between the position of the tracker and the target. Okay, now the tricky part. So how is this neural complexity that is based on TSE metric operationalized here? So for the individual complexity, we're basically looking at the mutual information of different subsets of nodes in the network. And normally, in a more complex scenario, you would be looking at all bipartitions of the network and then averaging and summing them to derive the complexity measure. In our case, we're focusing on just the sensory and the inner nodes, because the motor units basically are not functioning in the same way across conditions. So we wouldn't be able to compare this properly. And also for simplicity, we're only focusing on the one type of bipartition. So the inner node versus the rest, and then the other the inner node, so M2 versus the rest. And then we average this to have a measure of complexity. Then obviously the mutual information is based on the calculation of entropy for this subsets of neurons. And we also adopt another simplifying assumption, and we'll follow here previous work by Seth and Edelman, where we consider entropy to be computable from a covariance of the system under consideration. We can discuss, of course, the merits and disadvantages of all the simplifications in the discussion. So for the joint complexity, again, a very preliminary stab at operationalizing this dyadic complexity. So we're again looking at the bipartitions, but in the calculation of entropy, we're basing this on the sum of the covariance of aligned agent nodes. So it's still mutual information, but then it's kind of assuming that both agents are independent and we can just sum their covariances. So obviously, what we would like to have in future work is some kind of more of a shared measure of this joint complexity. But for now, so a co-information, but for now we're assuming that these two systems are independent. Okay, so what are the results? I will just mention some behavioral results and then the key, the neural complexity results. So as regards to evolved behavior, we actually have a lot of, so we tested 20 different seeds and a lot of the seeds converged. So it seems to be a relatively solvable task. We also see that in the generalist condition, actually, it converges a bit less. So perhaps this condition is a bit more difficult. And then for the evolved behavior, so as you've seen also in the visualization a few slides back, the agents are able to control the tracker to follow the target pretty well. So here on the bottom plot, you see the position over time of target and tracker. And it tends to kind of adopt this behavior of oscillating back and forth around the target position. And this is driven by the neural output being actually isomorphic to the required motor output and the required wheel performance. So here you have an example from the generalist case of agent 1 and agent 2. Jointly kind of alternating the neural output and then the resulting motor control. What I have to mention here, though, that this kind of neural activity is very typical of the generalist condition, but actually in the other conditions, both individual and the specialist case, it happens a lot that the agents figure out how to accomplish the task by effectively using just one neuron and leaving the other neuron kind of minimally or maximally active, but not doing much in the context of the task. And that might have implications for the results that you will see in a moment. Then we also looked just to see whether our results are compatible with previous work. So we looked at the evolution of this neural complexity measure, and we forced all simulations to start in the setting in which neural complexity would be 0. And we see that in the first 500 generations, it actually increases quite a lot and then stays relatively stable, which would be indicative of the agents finding the solution to the task, and then it kind of doesn't make sense anymore to create more complex activity. Then for the neural complexity, so we first have the individual level complexity results. And we found that in the generalist condition, complexity was significantly higher than in the other two conditions, so both individual and specialist. For the dyad level complexity, the result was actually mirrored. So obviously here you don't see the individual condition, just the social ones. And this dyad level complexity was still higher in the generalist case. So the conclusions are these. So you remember our hypotheses were that on the individual level, we will find that complexity is higher in both social conditions. compared to the individual, and in generalists higher than in specialists. And for the dyadic level, we predicted them this dyadic complexity to be relatively the same in both social conditions. However, our results showed that the generalists' complexity is much higher than both individual and specialist, and the specialists are actually comparable to the individual case, while for the dyadic level, the generalists are still higher than the specialists. So here you could wonder, of course, whether the different demands of the motor control could have something to do with it, because in the both in the specialist case, agents have to learn to control only one of the wheels, and therefore only one of the motor units. So maybe that is the reason why the complexity is so low. However, then you could argue that the generalists and the individualists should have comparable levels, because in both of these cases they're controlling both wheels, and which is not the case. So maybe there is something else going on here. Okay, so I have already briefly pointed at some limitations, but just to discuss it more in detail here. So complexity results do seem to depend on the number of inner neurons effectively used. So as I mentioned, in the generalist condition, almost all agents are using both neurons, while in the other conditions, a lot of them use only one. And of course, you could say, perhaps this measure actually dissolves into something like the number of neurons in the brain. And why didn't we just go for that metric? Well, we didn't want to go for it because it seems like you could have a smaller brain, but it's more efficient, or the processing is more complex. So we really want to investigate a measure that has more to do with the dynamics of brain activity rather than just the number of nodes. But in this case, maybe the two are correlated. So it's a question for future work to see whether maybe increasing the task complexity or the agent architecture would force the agents in all conditions to use all the nodes available, and whether then the results would be comparable to what we have achieved now. And then for the joint complexity measure, so we were really excited to try this out, but of course we made a number of assumptions here. So the assumption of Gaussianity, meaning that we're calculating entropy from covariance, and maybe this is not a good assumption for neural activity. And then we also made an assumption of agent independence, because we wanted to simplify this first attempt at operationalizing this measure, but maybe this has prevented us from finding a nonlinear result, so a result in which this joint complexity would not be mirroring, joint complexity result would not be mirroring the individual complexity result. Okay, and then kind of as a final conclusion and a warning, it seems that in general, behavioral, social, cognitive, and neural complexity are very tricky concepts. So even looking at empirical work, it seems you cannot really make sweeping statements about social complexity being related in a certain way to neural complexity, because it all depends, of course, on what you mean by each of these terms. But simulations hopefully can help us disentangle all the different ways we can talk about complexity and the relationship between all these concepts. So thank you.
Fantastic, another excellent talk. Do we have any questions, Katja? You can either put your hand up and I can unmute you and you can have a talky discussion, or please feel free to type in the Q&A, as I know lots of people have been doing already. So maybe I can ask a question while people get their typing on. So you talked about a number of assumptions in your final slide that you made, and you felt that they were limitations of your work. I was just wondering maybe if you could elaborate on what you would do differently if you're going to carry out future work. Are you currently doing future work in this area?
Yes, we are working very hard on this.
Yeah.
So maybe we can unmute Soheil, because he's more of an expert on this part of this work.
Yes.
Here is share again.
Absolutely. Oh, hang on. Where is Soheil? Okay, I'm going to allow you to talk, Soheil.
Well, thank you very much. Do you hear me?
Yes, perfect. Thank you.
Perfect. Thank you very much for this opportunity. Given the assumptions that Katya already outlined, one of the most important things for us at this point is moving away from more of the parametric statistics, something that has a specific type of assumption how the data might be distributed, which basically entails that how the agents might be actually behaving, towards something more non-parametric and allowing the system to find its own, or the statistics to find its own distribution, and then based on that, provide the results that can be more realistic and easier to interpret. So what we are doing at this point is first to move towards certain type of implementations of these measures of complexity that are non-parametric, and by that it means that looking into the data, deciding what type of the statistics are present in there, first moment, second moment, third moment, and based on that computing the complexities. Moreover, it would be also important to realize that as Katya also showed in one of the slides, we are not interested in individuals' cumulative contribution to the task, but basically what could be considered as of an integration of the task, which would be basically given the task, given the two agents, what are the, exactly, thank you, Katya. The one that we called it here as of co-information. So given the entire picture, the full picture, how the complexity, how the interactions, how the information generation and information processing changes. And in order to achieve that, basically, we need to remove all the assumptions that go with the covariations of the agencies, the additive assumption that comes basically as a part of the independence of the two agents, and then generate these results and reproduce them based on what we actually observe in the data itself. I hope that I addressed and answered that question. If more clarification is needed, please ask me.
Sorry, I forgot to unmute myself. No, sorry, that was fantastic. Thank you so much for your answer. I think we don't have any more questions, but obviously if people do think of some, I will keep Katya in the participants for a little bit, so you can type your questions and she can answer that.